Welcome. This is Sleepy Alchemy. Near the center of the galaxy, there is a molecule that smells of ripe fruit. It exists within molecular clouds whose chemistry has been quietly unfolding in that region for far longer than the Earth has existed, in conditions so cold and so still that the matter within them has had almost no reason to change. The temperature around it sits just a few degrees above the coldest point physics allows. There is nowhere you need to be. Tonight begins with that molecule. 100 details like it will follow. Small, exact facts about the matter the universe is made of. Some may surprise you. Most will simply pass through, quietly. You don't need to stay awake for any of them. That logic is very old and very quiet. There is a molecule, small by the standards of organic chemistry, called ethyl formate. Its molecular formula is C3H6O2. 3 carbon atoms, 6 hydrogen atoms, 2 oxygen atoms, arranged in a specific geometry that gives the molecule its particular chemical character. In laboratory analysis, ethyl formate has been associated with the volatile organic chemistry of certain ripened fruits, among other properties. It is not a rare compound. It is not exotic. It is the kind of molecule that exists quietly in the background of organic chemistry, present, measurable, following its own internal logic of bonding without any awareness that it is interesting. What makes it worth holding in mind tonight is not the molecule itself, it is where the molecule has been found. According to current astrophysical data, ethyl formate has been detected in dense molecular clouds near the center of the galaxy. Clouds of gas and dust so cold that, by available measurements, their temperature sits only a few degrees above the theoretical lower limit of temperature itself. Not the cold of a winter morning or the cold of a laboratory freezer. A cold so total and so sustained that chemical reactions which would ordinarily unfold in fractions of a second at room temperature are effectively brought to a halt. Bonds that would form in microseconds under warmer conditions instead sit in a state of suspended potential. The chemistry is present, the reactants are proximate, the energetic conditions required for completion simply do not exist. The molecules wait. Not patiently in any intentional sense. Molecules have no intent, that much we can say with confidence. But the physical outcome is indistinguishable from patience. A half-formed bond, a reaction caught mid-process, suspended in the cold the way sound is suspended in a room after the source has stopped. The vibration and the potential are there. The completion is simply deferred, perhaps indefinitely, by the absence of the thermal energy needed to push it forward. Ethyl formate on a dust grain in an interstellar molecular cloud sits in that suspension. Its carbon-oxygen bonds are intact. Its molecular geometry is unchanged. Its chemical identity has been preserved across timescales with no useful human equivalent. Not years, not centuries, not geological epochs, but something longer and quieter than all of those, measured by the slow drift of cold chemistry in the darkness between things. And the exploration begins there, not with scale, but with a single small molecule sitting very still in conditions that have given it no reason to change. That quality, the persistence of matter when there is insufficient energy to alter it, is the thread that runs through everything examined in this exploration. It appears in different materials, at different scales, under different physical conditions. But it is always the same underlying logic. Structure maintained not by any active process of preservation, but simply by the absence of the conditions required for change. Stability as the default, persistence as the natural state of matter when physics permits it. According to current scientific understanding, this holds true for molecules suspended in cold interstellar dust, for the crystal geometry of ice structures at low pressure and temperature, for the electron configurations of atoms that require no bond with any neighbor, for matter near absolute zero, where thermal energy diminishes to the point that quantum mechanics, always present, always governing, becomes the dominant description of what is actually occurring. And it holds true now, more quietly and more immediately, for the body resting here. The chemistry moving through a resting body is not dramatic. It is maintenance work, a low-energy cycle, structural repair, the slow exchange of molecules across membranes, the patient operation of processes that have been running without instruction and without any witnessing consciousness for far longer than any of this. The resting body is not doing nothing, it is doing the quietest version of everything. And the quietest version is, in many respects, the most fundamental one. None of this requires your attention to continue. You do not need to observe these processes for them to proceed. They will go on, measured, organized, complete enough as they are, for the entire duration of this exploration and long beyond it. The exploration itself will move slowly. 100 molecular details will pass through this space over the next few hours. Each one a small and precise piece of the physical world, offered without pressure, without urgency, without any requirement to retain, apply, or fully understand. Like someone moving through a very good museum late in the evening, when the rooms are nearly empty and there is no closing time to meet, pausing at whatever catches the attention, moving forward without ceremony, arriving nowhere in particular, except a little further along a quiet, unhurried path. The first detail is already here. A small molecule, 3 carbons, 6 hydrogens, 2 oxygens, sitting very still in the cold. Its bonds are intact. Its chemistry is suspended. It waits in the only sense that chemistry can wait, passively, without awareness, without expectation, for conditions that may or may not arrive. The only thing I ask of you as we travel this path together is that whatever is weighing on you, you let it rest behind you for now. Life has a way of pressing in on us, but tonight, on Sleepy Alchemy, you are here with us. And remember, whatever is happening out there, nothing matters more than you and your well-being. The deep, restful sleep that finds you tonight may be exactly what gives you the strength to face tomorrow's difficulties with a little more resilience, a little less exhaustion. So let's give our bodies this one kindness. Let's give them the rest they need. I hope you're comfortable wherever you are right now. If so, let's continue. The first thing to understand about matter in motion, before any figures are introduced or any specific molecules are named, is that motion at the molecular level is not the same thing as visible motion. A cloud of gas that appears perfectly still from any external vantage point is, according to current scientific understanding, filled with particles in ceaseless motion, colliding, rebounding, transferring energy from one to another in a process that never fully stops above the temperature of absolute zero. The appearance of stillness from the outside very often conceals an interior that is, at the molecular scale, quietly and continuously active. The details numbered 1 through 25 will move through the fluid dynamics of matter, specifically the behavior of gases and plasmas at the temperatures and pressures found in the large-scale structures of the observable universe. Not because these environments are the only places where these principles apply, but because they reveal the underlying physics at a scale where certain properties become visible in ways that would otherwise be too small or too brief to examine carefully. We begin with Secret 1. According to current physical models, plasma, the fourth state of matter, constitutes the vast majority of the observable baryonic matter in the known universe. It is not a rare or exotic state. It is the most common one. Plasma is what emerges when a gas is heated to the point where electrons are stripped from their parent atoms, releasing a mixture of free electrons and positively charged ions that respond collectively to electromagnetic fields. According to available data, the Sun is composed almost entirely of plasma. Most stars are. The matter between galaxy clusters is as well. The solid, liquid, and gaseous states that make up the material environment of everyday experience are, in this broader context, the rare conditions, a narrow thermal band in which electrons remain bound and molecules remain intact. Secret 2. The thermal conductivity of plasma, its capacity to transfer heat energy from one region to another, operates through mechanisms distinct from those found in solid or liquid materials. In a solid, thermal conductivity proceeds largely through lattice vibrations. Atoms bound within a fixed structure pass vibrational energy along the network. In a plasma with no fixed lattice present, heat energy is carried primarily by free electrons moving rapidly and colliding frequently, transporting energy with very little resistance to their motion. According to current plasma physics models, electron thermal conductivity in a fully ionized plasma can exceed that of most metals under the right conditions. Not because plasma is a better conductor in any structural sense, but because unbound electrons carry energy with remarkably little opposition. Secret 3. In the large-scale gas clouds found in the spaces between stellar systems, structures referred to in the astrophysics literature as the interstellar medium, the behavior of matter is governed by conditions with no direct equivalent in any laboratory environment on Earth. According to available data, the densities involved are extraordinarily low, in some regions containing fewer particles per cubic centimeter than the best vacuum achievable in most laboratory equipment. And yet, these clouds exhibit bulk properties that can be measured and described using the same fluid dynamics equations that apply to gases and liquids under familiar conditions. The equations do not change. The values of the variables within them become extreme. Secret 4. Viscosity, the property that makes honey move differently from water, a resistance to flow within a fluid, is a measurable quantity even in gases at very low densities. According to current physical models, the viscosity of a gas does not simply decrease because the gas is less dense. In fact, for an ideal gas, viscosity is largely independent of pressure across a wide range of conditions, a counterintuitive result derived analytically and later confirmed experimentally. What primarily changes viscosity in a gas is temperature. As temperature rises, gas molecules move faster, collide more energetically, and transfer momentum between fluid layers more effectively, increasing viscosity rather than reducing it. This is the inverse of the behavior seen in liquids, where higher temperatures typically lower viscosity. Secret 5. The temperature distribution within a large interstellar gas cloud is not uniform. According to current astrophysical data, different regions within the same cloud structure can vary in temperature by orders of magnitude, from just a few degrees above absolute zero in the densest, most sheltered interior regions, to thousands or tens of thousands of degrees in areas exposed to high-energy radiation from nearby sources. This temperature gradient drives material flows within the cloud, a process that rests, in essence, on the same thermodynamic principles that describe the movement of warm air rising from a heated surface. Secret 6. The concept of mean free path, the average distance a particle travels between collisions, scales dramatically with density. In ordinary air at sea level, the mean free path of a nitrogen molecule is on the order of tens of nanometers by standard calculation, short enough that each molecule undergoes billions of collisions per second. In the diffuse regions of an interstellar gas cloud, where densities are many orders of magnitude lower, the mean free path extends to distances measured in astronomical units. Individual atoms in these regions travel, on average, vast distances before interacting with another particle. The experience of solitude, in a physical sense, reaches a scale at which it becomes one of the defining characteristics of the medium. Secret 7. Despite those large mean free paths, the large-scale behavior of interstellar gas, when observed at sufficiently large scales, still satisfies the equations of fluid dynamics. The reason is that fluid dynamics as a discipline describes bulk properties, averages taken over large numbers of particles. At the scale of a molecular cloud spanning many light-years, even a very sparse gas contains enough particles for statistical averages to be meaningful and for the fluid approximation to hold. The individual behavior of any single atom is irrelevant to the description of the cloud as a whole. Secret 8. Magnetic fields play a significant role in the dynamics of ionized gas clouds, according to current astrophysical models. Because plasma is composed of charged particles, it interacts with magnetic fields in ways that neutral gases do not. A charged particle moving through a magnetic field experiences a force perpendicular to both its direction of motion and the field direction, a force described by the Lorentz equation. The collective result of this interaction across many particles is a tendency for plasma to flow along magnetic field lines rather than across them, producing structured, filamentary patterns in the distribution of material that can be observed in data from radio and infrared telescopes. Secret 9. The energy density of a magnetic field, the amount of energy stored per unit volume in the field itself, is a physically real quantity. And in regions of space where strong magnetic fields are present, this energy can be comparable to or exceed the thermal energy of the local gas. According to current models, the interplay between magnetic pressure and thermal pressure within interstellar gas clouds influences whether and how those clouds evolve over time. It is a balance of pressures that is not dramatic, not sudden, but persistent and defining. Turbulence, as a property of fluid motion, is observed in interstellar gas clouds across scales ranging from fractions of a light year to thousands of light years, based on current observational data. The turbulent motion in these clouds is not, in the colloquial sense, random, meaning it follows the statistical scaling laws that describe turbulence in all fluids, a relationship formalized in classical fluid mechanics and confirmed to apply even in these extreme, low-density, magnetized environments. The same mathematical structure that describes the churning surface of a fast-moving river appears in the velocity distribution of a molecular cloud. The physics, again, does not change, only the scale does. Secret 11. The cooling mechanisms in interstellar gas are dominated by radiation. Specifically, the emission of photons at particular wavelengths as excited atoms or molecules return to lower energy states. Current astrophysical data tells us that carbon monoxide is among the most effective coolants in cold molecular clouds, emitting photons at millimeter wavelengths as its rotational energy levels relax. This emission carries energy away from the cloud, allowing it to cool further. The efficiency of this cooling process depends on the abundance of carbon monoxide and the temperature of the gas, a feedback mechanism that, according to current models, shapes the thermal structure of molecular clouds across large scales. Secret 12. The concept of the sonic point, the location within a flow where the speed of material equals the local speed of sound, appears in the study of gas flows near compact objects and outflows from regions of intense energy release. The speed of sound in a gas depends on that gas's temperature and composition. It is not a fixed value, but a property of the medium. According to current models, in very hot, diffuse plasma near energetic astrophysical sources, the local speed of sound can be a significant fraction of the speed of light, not because the physics is exotic, but because temperatures are high enough that the thermal velocities of particles approach relativistic values. Secret 13. Pressure waves, compressions and rarefactions passing through a fluid medium, carry energy without permanently displacing the medium through which they travel. This is the basis of sound in air. A disturbance passes through, Molecules compress briefly and then return, and the pattern propagates forward. In interstellar gas, the same mechanism operates, but according to available data, the wavelengths and timescales involved are vastly extended. A pressure wave passing through a cold molecular cloud might have a wavelength of several light years and a period of millions of years. A sound in the broadest physical sense that no instrument could detect as a temporal sequence, only as a spatial pattern. I hope you're doing well, and that whatever fatigue or tension you are carrying is quietly dissolving. If this video is helping you in even a small way, that means everything to the Sleepy Alchemy channel. Before we continue, I want to say something directly. Whoever you are, wherever you are, you matter. I simply wanted you to know that. I hope you're finding the video restful. There's no requirement to track every detail. No obligation to give this your full attention. Molecular, precise, slow, passing through the air of this space the way heat moves through a gas, unhurried, gradual, a little at a time. The information is here. There's nothing to worry about. Secret 14. According to standard models of plasma behavior, when plasma cools sufficiently, free electrons begin to recombine with ions, a process called recombination, in which an ion captures an electron and releases the excess energy as a photon. This recombination emission produces characteristic spectra, the specific colors visible in the light of glowing gas clouds photographed by telescopes, and marks the transition of matter from the plasma state toward neutral gas. The photons released during recombination carry exactly the energy difference between the electron's initial and final states, a precise quantity determined entirely by the atomic structure involved. Secret 15. The energy carried by a single photon is related to its frequency through a constant, Planck's constant, h, a relationship that is exact and universal according to current quantum mechanics. Every photon of a given frequency carries the same amount of energy, regardless of where or when it was produced. A photon released during hydrogen recombination in a gas cloud billions of light years away carries the same energy as one released in a laboratory on Earth. Physics, in this respect, is among the most thoroughly confirmed unities in all of science. I hope this video and the information woven through it has helped you find some ease, and perhaps eased you gently toward sleep. Slowly, quietly, unhurried, we pick up where we left off. Continuing from Secret 16. According to current models of fluid dynamics in low-density environments, the concept of laminar flow, smooth, layered, turbulence-free motion, becomes increasingly theoretical at the scales and conditions found in diffuse interstellar gas. Real gas clouds, according to available observational data, exhibit velocity structures that reveal turbulent motion at nearly every scale an instrument can resolve. This is not a problem or an irregularity. It is the natural statistical behavior of a fluid system in which energy is continuously injected at large scales and dissipated at small ones, a cascade described mathematically by Kolmogorov's theory of turbulence, which applies whether the fluid in question is a flowing river, Earth's atmosphere, or a gas cloud spanning several light years. Secret 17. The Bernoulli principle, which describes the relationship between the velocity and pressure of a flowing fluid, holds for compressible gases with modifications that account for changes in density as the gas accelerates or decelerates. In high-velocity gas flows, such as those associated with outflows from energetically active regions studied in astrophysics, the compressibility of the gas becomes a dominant factor in the flow behavior, generating shock structures where the flow transitions abruptly from supersonic to subsonic speeds. These shock fronts are, according to current models, sites of significant chemical activity, regions where molecular bonds are broken and reformed, where temperatures spike briefly before subsiding, and where the chemistry of a gas cloud can change substantially within a relatively narrow band of space. Secret 18. The diffusion of one species of gas into another, the process by which a drop of dye spreads through still water, or the warmth of something heated disperses through a cool room, is described by Fick's laws of diffusion, which relate the flux of a substance to the concentration gradient driving its motion. In interstellar gas clouds, according to current models, diffusion operates across timescales that are imperceptible by any experiential standard. Individual molecular species mixing and redistributing through a cloud over millions of years. The equilibrium toward which diffusion tends is simply a more uniform distribution of matter. Spreading, gradual equalization, quiet and inevitable, and very, very slow. Secret 19. Thermal pressure, the outward force exerted by a gas as a result of the kinetic energy of its particles, works against gravitational attraction in any self-gravitating gas cloud. According to current astrophysical models, the balance between these two forces determines whether a gas cloud remains in a relatively stable configuration over time or undergoes a net change in its structure. The physics of this balance is described by a relationship known as the virial theorem, a broadly applicable result of classical mechanics that connects the average kinetic and potential energies of a bound system. The virial theorem applies to gas clouds and also, with different variables, to galaxy clusters, to the internal structure of stars, and to the behavior of molecules within a fluid. The same mathematical relationship, different contexts, the same underlying logic. Secret 20. The specific heat capacity of a gas, the amount of energy required to raise its temperature by a given amount, depends on the molecular structure of the gas in question. Monatomic gases, composed of single atoms, store thermal energy only in the translational motion of those atoms. Diatomic gases, composed of two-atom molecules, such as molecular hydrogen, can additionally store energy in rotational and vibrational modes, giving them a higher heat capacity. According to current thermodynamic models, the heat capacity of a gas is therefore a fingerprint of its molecular architecture, a macroscopic, measurable property that encodes information about the internal structure of the molecules it comprises. Secret 21. According to available data, In the cold, dense interiors of molecular clouds, molecular hydrogen is the dominant chemical species, far more abundant than any other molecule. Because hydrogen is the simplest atom, one proton, one electron, the molecule it forms, H2, is structurally simple as well. Two atoms bonded by a shared electron pair, with a bond energy and bond length measured precisely in laboratory conditions. In cold clouds, H2 sits in extremely low rotational energy states, contributing very little to the cloud's thermal energy and serving essentially as the structural background against which the chemistry of less abundant molecules plays out. Secret 22. According to available data, the chemistry that occurs inside cold molecular clouds, where temperatures sit 10 to 30 degrees above absolute zero, proceeds almost exclusively through ion-molecule reactions. Reactions initiated when a cosmic ray or energetic photon ionizes a molecule, producing a reactive ion that then reacts with a neutral molecule it encounters. These reactions are effective at low temperatures in ways that neutral-neutral reactions are not, because they do not require the colliding species to overcome an energy barrier. The reactants are brought together by the electrostatic attraction between the ion and the induced dipole of the neutral molecule, a gentle, long-range force that makes the reaction possible even when very little thermal energy is available. Secret 23. According to current models of interstellar chemistry, ethyl formate and related organic molecules in cold cloud environments are thought to form primarily on the surfaces of dust grains, small solid particles composed of silicates and carbonaceous material distributed throughout molecular clouds. The surface of a dust grain provides a substrate on which atoms and simple molecules can land, be held at low temperatures, accumulate, and react in ways that would not be possible in the gas phase. The grain's surface acts in this chemical model as a kind of slow workbench, one that gathers reactants and holds them in proximity long enough for bonds to form even in the near-total absence of thermal energy. Secret 24. Organic molecules assembled on grain surfaces are, according to current models, eventually returned to the gas phase when the grain is heated, either through the absorption of radiation or through other heating mechanisms. At that point, the molecules desorb from the surface and enter the surrounding gas, where they can be detected spectroscopically. The sequence, gas phase atoms landing on grain surfaces, reacting slowly, being released back into the gas phase, represents a chemical cycle operating across timescales of thousands to millions of years, governed at each stage entirely by the physics of surface adsorption, low-temperature reaction kinetics, and thermal desorption. No direction, no intent. Simply chemistry following its own internal logic, wherever that logic leads. Secret 25. The concept of chemical equilibrium, the state in which the forward and reverse rates of a chemical reaction are equal, producing no net change in composition, is, according to current models, rarely, if ever, achieved in interstellar molecular clouds. The timescales required to reach equilibrium frequently exceed the timescales over which the cloud's physical conditions remain stable. The cloud changes in density, in temperature, in radiation exposure, faster than its chemistry can fully respond. What is observed, therefore, is not equilibrium chemistry, but something more nuanced, a chemistry that is perpetually in transition, never fully settled, always somewhere midway between one state and another. The process continues quietly, in no hurry to resolve itself. We've moved through the first 25 secrets slowly, without asking anything of you. There is no need for you to hurry either. Simply resting is enough. Nothing matters more than you do. Whatever daily concerns you're carrying, set them aside for now. It's not worth exhausting yourself over things beyond your control. Tonight, you've come to this video to rest and perhaps learn something along the way. Or perhaps the reason is different. Perhaps you simply wanted a quiet voice in the background to ease you toward sleep. Whatever brought you here, I'm genuinely glad you chose to spend this time with Sleepy Alchemy. Now the exploration shifts. We move into an entirely different state of matter. Nothing flows here. Nothing drifts the way gases do. Everything is, in a sense, locked in place. This is the world of crystals, where, unlike in gases, everything is arranged with mathematical precision. Let's begin with the most familiar crystal of all, ice. But take your time. We're not talking about the ice in your glass. We're talking about ice in the far reaches of the universe, stranger and more varied than the word usually suggests. Secret 26. Water ice, the crystalline solid form of H2O, organizes its molecules in its most common form, known as ice 1H, into a hexagonal lattice structure. In this arrangement, each water molecule is bonded to 4 neighboring molecules through hydrogen bonds, weak electrostatic attractions between the slightly positive hydrogen atoms of one molecule and the slightly negative oxygen atom of another. These hydrogen bonds are not covalent bonds. They are considerably weaker. But they are directional. They point along specific geometric orientations, and it is this directionality that gives water ice its open hexagonal lattice, its density lower than that of liquid water, and the characteristic geometry of snowflake formation, which reflects the 6-fold symmetry of the underlying crystal lattice. Secret 27. At very low pressures and temperatures, conditions found in certain regions of interstellar space and in the outer atmospheres of some planetary bodies, water molecules can condense directly from gas to solid without passing through a liquid phase in a process called deposition. According to current physical models, under these conditions, ice forming at very low temperatures and without the organizing influence of liquid water is often amorphous rather than crystalline. The water molecules solidify without having time to arrange themselves into a regular lattice. Amorphous ice may, according to available data, be the most abundant form of water in the observable universe, though it is rarely what comes to mind when the word ice is used. Secret 28. The optical properties of ice crystals, the ways they interact with light, depend on the geometry of the crystal lattice and the material's refractive index, which is itself a function of the molecular structure and density of the solid. In crystalline ice, the regular spacing of molecules creates conditions for specific interference effects as light passes through or reflects from the material. The halos and arcs occasionally visible in Earth's sky when thin clouds of ice crystals are present are direct consequences of Ice 1H's hexagonal geometry. Light refracted through the 60-degree and 90-degree faces of hexagonal prisms and plates at angles determined entirely by the crystal geometry and the refractive index of ice at visible wavelengths. Secret 29. According to available data, in the outer regions of certain planetary systems, temperatures are low enough for molecules other than water to exist as ice on solid surfaces. Methane, CH4, the simplest organic molecule, freezes at approximately 91 Kelvin at standard pressure and is found as surface ice on some distant planetary bodies. In its solid form, methane molecules settle into a crystalline structure held together by van der Waals forces, weak, non-directional attractions arising from temporary fluctuations in electron distribution. These forces are considerably weaker than the hydrogen bonds that hold water ice together, which is reflected in methane ice's much lower melting point compared to water ice. Secret 30. The reflectivity of a surface, the fraction of incident light it reflects rather than absorbs, is, for crystalline ices, a function of the crystal structure, the grain size of the ice, and the presence or absence of impurities within the crystal lattice. Fresh, uncontaminated crystalline ice has high reflectivity at visible wavelengths. It appears bright because it reflects most of the light that reaches it. According to current models, as ices in space age and accumulate radiation exposure, their optical properties change. Absorbed radiation alters the molecular structure, creating new chemical bonds and color centers within the crystal that reduce reflectivity at certain wavelengths. Over timescales measured in millions of years, the surface darkens gradually. The room is quieter now than when this began, or perhaps the quiet was always this complete, and the exploration has simply made it easier to notice. The molecules in the air of this room follow the same physics, colliding, transferring energy, settling into the distribution of speeds and positions that the room's temperature permits. They are not listening, they are simply here, doing what matter does, continuing, exchanging, carrying their molecular architecture a little further forward with each passing moment. Before we go on, I want to pause briefly. As I always say, rest, because everything is better when you're at ease. It may be that right now there's something you've been working on, something you haven't been able to fix or resolve, and stepping back, truly resting, giving yourself a moment of genuine calm, you might find that when you look at it again from that quieter place, you can actually see it whole. What I mean is that simply being at rest can free us from so much of what weighs on us. And when I say rest, I don't mean abandon your responsibilities or stop caring. I mean the opposite. A rested, settled, clear mind can work through things that feel impossible when we're tense. Even falling asleep requires ease. You have to be calm enough to let go. And I want you to know this too. You are valuable. You are unique. Never let that light burning inside you go out. Let's continue. We travel now slowly into the deeper architecture of the crystal world. From Secret 31 through to Secret 50, a quiet and vast structure unfolds. There is no need to listen carefully to any of this or to commit it to memory. Let each word, each detail, each piece of information arrive the way a gentle, cool breeze comes through an open window, touching you softly and then moving on. Nothing is being asked of you. Simply listening, simply feeling is more than enough, and only if you wish. Secret 31. Carbon dioxide ice, dry ice in everyday usage, forms a crystalline solid in which CO2 molecules are arranged in a face-centered cubic lattice. Unlike water ice, carbon dioxide molecules do not form hydrogen bonds with one another. The intermolecular forces holding CO2 ice together are entirely van der Waals in character. This structural difference means that CO2 ice sublimates, passing directly from solid to gas at temperatures far below those at which water ice melts under standard pressure conditions. According to available data, on planetary surfaces where CO2 ice is present, seasonal temperature shifts can drive large-scale cycles of sublimation and redeposition, effectively transporting material from one region of the surface to another through the atmosphere over extended periods. Secret 32. The molecular geometry of carbon dioxide, a linear molecule with the carbon atom centered between two oxygen atoms at an exact bond angle of 180 degrees, means that despite having polar covalent bonds, the molecule has no net dipole moment. The polarity of each carbon-oxygen bond is exactly canceled by the equal and opposite polarity of the other. This geometric cancellation has direct consequences for the intermolecular forces available to CO2, and therefore for its physical properties, its melting point, its boiling point, its solubility in various solvents, and the structure of its crystalline solid form all reflect in measurable ways the outcome of that single geometric fact about the shape of the molecule. Secret 33. Nitrogen ice found on the surfaces of certain distant planetary bodies, according to current observational data, presents a particularly interesting case of a molecular crystal in which the sole cohesive mechanism is the weakest category of van der Waals interaction, known as London dispersion forces. Nitrogen molecules, being nonpolar and symmetric, have no permanent dipole and no capacity for hydrogen bonding. The only attraction between them arises from instantaneous, temporary fluctuations in electron distribution that induce complementary fluctuations in neighboring molecules. These forces are real, measurable, and entirely sufficient to produce a crystalline solid, simply one that requires very low temperatures to remain stable. Secret 34. The thermal conductivity of crystalline solids is, according to current models of solid-state physics, carried by quantized lattice vibrations called phonons. A phonon is not a particle in the conventional sense. It is the quantum of vibrational energy propagating through a crystal lattice, in the same way that a photon is the quantum of electromagnetic energy. The rate at which thermal energy moves through a crystal depends on how freely phonons can propagate through the lattice, how far they travel before being scattered by lattice defects, impurities, or other phonons. In a perfect crystal at low temperature, phonon mean free paths extend considerably, and thermal conductivity increases significantly. This is one reason why certain highly ordered crystalline materials are used in applications that require efficient heat transfer. Secret 35. The optical reflectance spectra of methane crystals, the precise fraction of incoming light reflected at each wavelength, have been measured under laboratory conditions and are used in current models to interpret observational data from distant planetary surfaces. Methane ice reflects strongly at visible wavelengths, but absorbs at specific near-infrared wavelengths corresponding to the vibrational modes of the CH4 molecule. The pattern of absorption features in the reflected light functions again as a molecular fingerprint. The same spectroscopic logic that identifies ethyl formate in a galactic gas cloud also identifies methane ice on a planetary surface billions of kilometers away. The method is universal because the physics is universal. Secret 36. Mixed ices, crystalline solids containing two or more molecular species within the same matrix, can exhibit properties that differ significantly from their pure component ices. Water and methanol, for instance, when co-deposited as amorphous ice at low temperatures and subsequently warmed, can undergo chemical reactions between the two species during the warming process that would not occur in the gas phase at those temperatures. The ice matrix, which holds molecules in close proximity over extended periods, effectively lowers the activation barrier for certain reactions, a phenomenon with direct implications for the inventory of complex organic molecules that can accumulate in cold astrophysical environments over time. Secret 37. Clathrate hydrates are crystalline structures in which water molecules form hydrogen-bonded lattice cages, and small guest molecules, methane, carbon dioxide, noble gases, are trapped within those cages without forming chemical bonds with the surrounding water framework. The guest molecules are held in place solely by the cage geometry and weak van der Waals interactions with the cage walls. According to current models, clathrate hydrates are stable under specific combinations of temperature and pressure, and their formation and dissociation influences the chemical cycling of gases in a range of planetary and astrophysical environments. Secret 38. The concept of lattice energy, the energy required to completely separate a crystalline solid into its constituent gaseous ions or molecules, provides a quantitative measure of a crystal's stability. Higher lattice energy means a more stable crystal, one that requires greater energy input to disrupt. For ionic crystals, lattice energy depends on the charges and sizes of the ions involved. For molecular crystals, it depends on the strength of the intermolecular forces. Lattice energy cannot be measured directly in a single experiment, but according to current thermochemical models, it can be calculated precisely from a cycle of measurable quantities, providing a reliable picture of the energy landscape of the solid state. Secret 39. Defects in crystal lattices, deviations from perfect periodic order, are, according to solid-state physics, not simply flaws, but structurally significant features that affect the mechanical, electrical, and optical properties of materials in ways that a perfect lattice would not predict. A vacancy, a missing atom in an otherwise regular lattice, alters the local stress distribution and can facilitate the diffusion of atoms through the solid. An interstitial, an atom occupying a position between regular lattice sites, elastically deforms the surrounding lattice. These defect structures are present in all real crystals and, in many cases, are deliberately introduced to engineer specific material properties. Secret 40. The phenomenon of birefringence, the splitting of a light beam into two components with different refractive indices as it passes through certain crystalline materials, arises from the anisotropy of the crystal structure. The fact that the arrangement of atoms or molecules is not the same in all directions. In a birefringent crystal, the speed at which light propagates depends on the direction of propagation relative to the crystal axes and on the polarization of the light. This directional dependence of optical properties is a direct macroscopic consequence of the underlying molecular geometry. Another instance of atomic scale structure producing effects measurable at scales accessible to ordinary observation. The secrets through to 30 followed the geometry of cold, locked matter, how molecules arrange themselves into ordered structures when thermal energy is reduced sufficiently, and how those structures interact with light, with heat, and with other molecules they encounter. We are not hurrying. We continue gently. All that sleepy alchemy asks as it passes these details along one by one is that you find your way quietly toward sleep. There is no need to focus on any of this information. Focusing on sleep is all that matters. Now we leave the ordered world of crystals and turn our attention to the quiet, self-contained realm of individual atoms. The secrets from 41 through to 50 concern what may be matter's most elegant quality, its capacity for wholeness. Chemical stillness. There are atoms that require nothing from the outside, no bond, no partner, no external influence. They exist completely on their own, wholly intact. This is not a limitation. It is an expression of internal completeness. Their electrons are arranged with such precision that they neither seek anything from neighboring atoms nor have anything to offer them. Atoms that are, in their own inner world, entirely at peace. Secret 41. The chemical inertness of gold, its resistance to corrosion and oxidation under ordinary conditions, is, according to current quantum chemistry, a consequence of its electron configuration and, more specifically, of a quantum mechanical effect called relativistic contraction. Gold's nucleus contains 79 protons, creating a powerful nuclear charge. According to the model, electrons moving in orbitals near that nucleus travel at velocities at which relativistic corrections to their mass and energy become significant. The primary effect relevant to gold's chemistry is the relativistic contraction and stabilization of gold's outermost 6s valence orbital, the orbital from which an electron would need to be removed or shared in order for oxidation to occur. This relativistic stabilization raises gold's ionization energy above that expected from its position in the periodic table, making the energy cost of oxidation higher than the surrounding chemical environment can supply under ordinary conditions. Secret 42. The stability described by quantum chemistry models for gold is not absolute. Gold does form compounds under sufficiently extreme conditions and with sufficiently reactive partners. But across the range of temperatures, pressures, and chemical environments found on Earth's surface and in the near vacuum of space, gold's resistance to oxidation is, according to available data, effectively complete. A sample of pure gold left at room temperature, in seawater, in soil, in open air, does not develop an oxide layer. The surface chemistry that gradually degrades iron, copper, silver, and most other metals simply does not proceed for gold under those conditions. The bond energy required to initiate the oxidation reaction is not available in the surrounding environment. Secret 43. The concept of bond energy, the energy required to break a chemical bond, provides a quantitative framework for understanding why certain materials persist while others degrade. Diamond, the crystalline form of carbon in which every atom is covalently bonded to 4 neighbors in a tetrahedral arrangement, owes its exceptional hardness and chemical stability not to any single bond having record-breaking energy, but to the architecture of the crystal as a whole, a 3-dimensional network of strong, short carbon-carbon bonds extending uniformly in all directions, with no weak planes, no structural gaps, and no sites of reduced bonding. There is no path through the crystal that does not pass through strong covalent bonds. The same carbon atoms arranged differently, as in graphite, produce a material with markedly different mechanical and chemical properties, demonstrating that what determines a material's behavior is not only the identity of its atoms, but the geometry of their bonding. The room is still. Matter has been moving through it slowly, settling the way sediment settles through calm water, each detail descending quietly, without disturbance, without effort, arriving exactly where it will. The video continues in that same quiet way. And if the body has grown heavier during this time, it is doing so now without being asked, carrying out what it carries out when nothing is required of it. Any detail or secret offered here, when it is soft enough, slow enough, and unhurried enough, fills the mind without straining it, passing through without weight, without demand. Before we continue, I want to speak to you sincerely as a friend, as someone who genuinely wants to share in whatever you might be carrying. I know that life sometimes brings things we didn't plan for and didn't ask for. Even so, I want to ask something of you, to keep finding your strength and to keep moving through whatever is weighing on you. Every time you lie down and let sleep come, remember, you are capable of handling whatever life places in front of you, because you are singular, you are worth something, and never give life permission to break you. Whatever today brought that was difficult or unwelcome, let tonight's sleep take it from your shoulders. Rest of real quality matters more than most things when it comes to facing what's ahead. So as you continue into that quiet, restful sleep, let me continue with the rest of what remains. Secret 44. The electron configuration of a noble gas represents, according to current quantum mechanical models, a state of complete outer shell occupancy, what chemists describe as a full valence shell. For helium, this means 2 electrons filling the first shell entirely. For neon, 8 electrons completing the second shell. For argon, 8 electrons in the s and p sublevels of the third shell. In each case, the outermost electrons are arranged in a configuration that neither readily accepts additional electrons nor releases the ones it has. The energy cost of disturbing that arrangement exceeds what ordinary chemical environments can supply. The result is an atom that passes through matter, through air, through plasma, through molecular clouds, without forming bonds, without reacting, without leaving any chemical trace of its passage. Secret 45. Helium, the lightest of the noble gases, has, according to available data, the lowest boiling point of any known substance at standard pressure, approximately 4 Kelvin. Below that temperature, helium transitions from gas to liquid, but at standard pressure, it will not solidify at any temperature, no matter how low. Producing solid helium requires the application of external pressure in addition to near absolute zero temperatures, a minimum of around 25 atmospheres. This behavior is a consequence of quantum mechanical zero-point energy. Even at absolute zero, helium atoms retain residual vibrational energy sufficient, given the very weak van der Waals forces between helium atoms, to prevent the formation of a stable lattice without external compression. Secret 46. The quantum mechanical basis of noble gas inertness is described, according to current atomic theory, through the concepts of orbital symmetry and electron screening. The filled outer shells of noble gas atoms create a spherically symmetric electron density distribution, a smooth, uniform cloud of negative charge surrounding the nucleus. This symmetry makes it energetically unfavorable for another atom to approach closely enough to form a bond. The electrons of the approaching atom experience repulsion from the outer electron cloud before any attractive interaction with the nucleus becomes significant. The noble gas atom presents in this model a closed and complete surface, not hostile, simply self-sufficient. Secret 47. Under sufficiently reactive chemical conditions, noble gases can be forced to form compounds, genuine exceptions to the general rule of noble gas inertness. Xenon difluoride, for instance, is a stable compound formed between xenon and fluorine that can be synthesized at ordinary atmospheric pressure simply by exposing the two gases to ultraviolet light. What makes this reaction possible is not extreme pressure, but the exceptional electronegativity of fluorine, one of the most reactive elements known, with sufficient capacity to pull electron density from even xenon's stable outer shell. These compounds represent genuine exceptions consistent with quantum mechanical models. Given a sufficiently reactive partner, the energy barrier against bond formation can be overcome, even for atoms whose configurations strongly resist it. The rule holds under ordinary conditions with ordinary chemical partners. The exceptions exist at the limits of chemical reactivity. Secret 48. Neon, despite being the second most abundant noble gas in the observable universe, according to current astrophysical estimates, is, according to available data, relatively rare in Earth's atmosphere compared to argon. This discrepancy does not reflect any difference in the fundamental chemistry of the two elements. Both are inert. Both accumulate in environments where they cannot react. The difference lies in how much of each was incorporated into the planetary body and subsequently released. A geological and geochemical story, not a chemical one. The neon itself has not changed. It carries the same electron configuration it has always carried. Secret 49. The ionization energy of an atom, the energy required to remove one electron from a neutral atom in the gas phase, is highest among the elements of any given period in the periodic table for the noble gases. This directly reflects the stability of the full outer shell configuration. Removing an electron from a noble gas requires disrupting a complete and energetically favorable arrangement. Helium has the highest first ionization energy of any element. Neon, argon, krypton, and xenon follow the same pattern within their respective periods. Highest ionization energy, greatest resistance to electron removal, most chemically inert. The periodic table is, in this sense, a map of chemical willingness, and the noble gases occupy its most reluctant edge. Secret 50. The use of noble gases in practical applications, lighting, welding, cryogenics, medical imaging, is entirely built upon the property examined here. Argon is used as an inert shielding gas in welding because it prevents reactive atmospheric gases, oxygen and nitrogen, from interacting with the hot metal at the weld site. Helium is used in cryogenic applications because of its uniquely low boiling point. Neon, when electrically excited, produces its characteristic light emission, not because it reacts with anything, but because its electrons absorb energy, transition to higher energy levels, and release photons of specific wavelengths as they return to the ground state. Inertness is not the limitation, it is the useful property. The atom gives light without giving itself. We have now moved through 50 of the 100 secrets, exactly half. 50 secrets have passed quietly through the room. We have covered fluid dynamics, crystal geometry, chemical stability, atomic configuration. We have moved slowly. As I always say, there is no need to hold on. What comes next goes deeper still, into the territory where temperature begins to approach its own theoretical lower limit, and where matter's behavior changes in ways that no longer require classical physics to describe, but quantum mechanics, because the familiar forms of friction, resistance, and boundary no longer apply in the ways we know. The secrets from 51 to 100 will follow what happens to matter as thermal energy is gradually withdrawn. The slowing of electrons, the onset of quantum coherence, the transition into states of matter where the ordinary rules of friction, resistance, and boundary no longer apply in their familiar forms. Before we reach Secret 51, I want to say this. If you are still here, still watching, then something in this is reaching you, and that means everything to me. Perhaps you're already asleep. Perhaps your eyes are growing heavy, and sleep is beginning to arrive. Or perhaps you're still awake. Either way, I want you to know something. Life does not always treat us as we deserve. Sometimes things happen that we haven't earned and didn't ask for. Sometimes we want something deeply, work for it honestly, and still don't reach it. All of that is normal. That is what life is. The thing you've been hoping and working toward may not, in the end, be what's truly right for you. Perhaps one day a door will open that makes everything you were reaching for look small by comparison. That's why it matters. Letting go of the grief over what hasn't come and learning to see the chances that are still arriving, the doors that are still opening. Because if we exhaust ourselves mourning what we wanted and didn't get, we may not be able to see what's still on its way. I say this with complete sincerity because I am living it myself. I hope I've managed to carry that thought across to you and to leave you feeling even slightly better. If so, good, then let's continue. Secret 51. As temperature decreases toward absolute zero, the theoretical point at which all classical thermal motion ceases, 0 Kelvin, quantum mechanical effects become increasingly dominant in the behavior of matter. This is not because quantum mechanics switches on at low temperatures and fades at high ones. Quantum mechanics governs matter at all temperatures. But at ordinary temperatures, the quantum behavior of individual particles is masked by the large thermal energies that drive familiar, classical statistical behavior. As thermal energy is reduced, the quantum character of particles, their wave-like properties, their discrete energy levels, their tendency toward collective quantum states, becomes the primary description of what is actually occurring. Secret 52. The third law of thermodynamics states, according to current physical models, that the entropy of a perfect crystal approaches zero as temperature approaches absolute zero. Entropy, in thermodynamic terms, is a measure of the number of microscopic arrangements available to a system, a measure of molecular disorder. At absolute zero, in the ideal case, only one arrangement exists, every particle in the lowest possible energy state, perfectly ordered. The entropy of that state is, by definition, zero. This theoretical limit cannot be reached in practice. No physical system can be cooled all the way to absolute zero. But it defines the direction in which matter moves as thermal energy is gradually removed, toward greater order, toward fewer available states, toward lower entropy. Secret 53. The process of laser cooling, through which atoms can be slowed and cooled to temperatures within billionths of a degree of absolute zero, depends on the momentum carried by individual photons. When an atom moving in a particular direction absorbs a photon moving in the opposite direction, it absorbs the photon's momentum along with its energy. The atom slows slightly. If the process is repeated many times, using carefully tuned laser light that the atom preferentially absorbs when it moves toward the source, the atom can be slowed to velocities corresponding to temperatures in the microkelvin or nanokelvin range. According to current experimental data, this technique has produced some of the coldest matter ever measured, colder than any naturally occurring environment documented in the observable universe. Secret 54. At temperatures in the nanokelvin range, certain collections of atoms can undergo a transition into a state called a Bose-Einstein condensate, a quantum state in which a large fraction of the atoms simultaneously occupy the lowest available energy level and begin to behave not as a collection of independent particles, but as a single quantum entity. The condensate was predicted theoretically decades before it was first produced experimentally, and its eventual realization confirmed predictions made on the basis of quantum statistical mechanics. In a Bose-Einstein condensate, the individual identities of atoms effectively dissolve into the collective quantum state, a macroscopic expression of quantum behavior with no classical analog. Secret 55. Superfluidity, the property by which certain substances, cooled below a critical temperature, flow without any measurable viscosity, is, according to current quantum mechanical models, a consequence of the same physics that underlies Bose-Einstein condensation. Liquid helium-4, when cooled below approximately 2.17 Kelvin at standard pressure, transitions into a superfluid state in which it flows without resistance through arbitrarily narrow channels, climbs the walls of its container, and maintains continuous circulation in a closed loop indefinitely once initiated. None of these behaviors have any classical explanation. They are direct manifestations of the quantum mechanical wave character of helium atoms, which become sufficiently coherent at that temperature to flow collectively without the scattering events that produce viscosity in ordinary liquids. Secret 56. The specific temperature at which helium-4 undergoes the transition to superfluidity is called the lambda point, named for the shape of the curve describing the heat capacity of liquid helium as a function of temperature near that transition. At the lambda point, the heat capacity of the liquid rises sharply and then drops abruptly, forming a curve that resembles the Greek letter lambda when plotted. This singular point in the heat capacity reflects the underlying phase transition, a collective reorganization of the quantum state of the liquid propagating through the entire sample simultaneously, a change with no spatial boundary separating the old phase from the new. We now continue from Secret 57 onward. What remains will be offered the same way everything before it has been, slowly, without hurry, without asking anything of you. Secret 57. Superconductivity, the phenomenon by which certain materials, cooled below a critical temperature, conduct electrical current with absolutely zero resistance, shares, according to current condensed matter physics, a conceptual foundation with superfluidity. In a conventional superconductor, electrons near the Fermi energy form paired quantum states called Cooper pairs, held together not by the direct electrostatic repulsion that would ordinarily exist between two negatively charged particles, but by an indirect interaction mediated through the lattice vibrations of the surrounding crystal. These paired electrons behave collectively as a quantum fluid, flowing through the material without the scattering events that produce electrical resistance in ordinary conductors. Secret 58. The energy gap that opens in the electron structure of a superconductor below its critical temperature is, according to current BCS theory, named for the physicists who developed it, directly related to the binding energy of the Cooper pairs. This gap means that the condensed electrons cannot be scattered into slightly different energy states by the small perturbations that would disrupt ordinary conduction. The scattering events that constitute electrical resistance in a normal metal simply have no available final states to scatter into. The current continues uninterrupted because the quantum structure of the paired state leaves no room for the disruptions that resistance requires. Secret 59. The Meissner effect. The expulsion of magnetic fields from the interior of a material as it transitions into the superconducting state is, according to current models, a defining property of superconductivity that distinguishes it from perfect conductivity alone. A perfect conductor would preserve whatever magnetic field existed when its resistance dropped to zero. A superconductor actively expels magnetic flux from its interior regardless of the field's prior history. A spontaneous reorganization of the material's electromagnetic environment that reflects the underlying quantum coherence of the superconducting state. The expulsion is complete, precise, and reproducible. Secret 60. As matter approaches absolute zero, the quantum mechanical uncertainty principle, which states that the position and momentum of a particle cannot both be known simultaneously to arbitrary precision, prevents particles from coming fully to rest even at the theoretical temperature limit. The residual energy associated with this quantum constraint is called zero-point energy. It is not thermal energy. It cannot be removed by cooling further, but it is real, measurable in its effects, and is the reason helium remains liquid all the way to absolute zero at atmospheric pressure. The zero-point energy of helium atoms is large enough, relative to the weak van der Waals forces between them, to prevent solidification without additional external pressure. Secret 61. Quantum tunneling, the ability of a particle to pass through an energy barrier that classical mechanics would say it lacks sufficient energy to cross, becomes increasingly significant as temperatures approach absolute zero and thermal energies diminish. In this regime, the wave-like character of particles is dominant, and the probability of finding a particle on the far side of a barrier is determined by the width and height of the barrier relative to the particle's de Broglie wavelength. Tunneling has measurable consequences in low-temperature chemistry. Certain reactions that would be classically forbidden near absolute zero proceed at small but non-zero rates because the reactants tunnel through rather than over the activation energy barrier. Secret 62. The de Broglie wavelength of a particle, the wavelength associated with its quantum mechanical wave character, increases as the particle's momentum decreases, which occurs as temperature falls. At ordinary temperatures, the de Broglie wavelengths of atoms are far smaller than the distances between them, and quantum effects on their spatial distribution are negligible. As temperatures drop into the micro-Kelvin range, the de Broglie wavelengths of atoms can become comparable to the distances between them. At that point, the wave functions of neighboring atoms begin to overlap, and the quantum statistical properties of the ensemble, whether the atoms are bosons or fermions, begin to govern the macroscopic behavior of the material. Secret 63. The distinction between bosons and fermions, the two fundamental categories of quantum particles, is determined by a quantum mechanical property called spin. Particles with integer spin values are bosons. Particles with half-integer spin values are fermions. Bosons can occupy the same quantum state simultaneously. This is what makes Bose-Einstein condensation possible. Fermions cannot. They obey the Pauli exclusion principle, which states that no two identical fermions can occupy the same quantum state at the same time. This single rule is responsible, according to current quantum mechanics, for the structure of atoms, the stability of matter, the existence of distinct chemical elements, and, at the extreme densities found in collapsed stellar remnants, the electron degeneracy pressure that prevents white dwarf stars from collapsing further under gravity. The exclusion principle does not merely govern the small, its consequences extend to the architecture of stars. Secret 64. Fermionic superfluidity. Superfluidity in systems composed of fermions rather than bosons requires the fermions to first pair up, forming composite particles that can behave as bosons and subsequently undergo condensation. In liquid helium-3, which is composed of fermionic helium atoms rather than the bosonic helium-4 atoms that become superfluid at 2.17 Kelvin, superfluidity occurs at a much lower temperature, approximately 2 millikelvin, through a pairing mechanism analogous to Cooper pairing in superconductors. The underlying physics is the same. The temperature required is far lower because the pairing interaction in helium-3 is considerably weaker than the phonon-mediated interaction in metallic superconductors. Secret 65. The specific heat capacity of a solid at low temperatures follows, according to current solid-state physics, the characteristic temperature dependence predicted by the Debye model of lattice vibrations, proportional to the cube of the absolute temperature. This cubic dependence reflects how phonon populations scale with temperature. As temperature decreases, fewer vibrational modes are thermally populated, and the heat capacity falls towards zero in accordance with the third law of thermodynamics. The Debye model captures the essential physics through a relatively simple approximation, treating the crystal as a continuous elastic medium with a maximum phonon frequency determined by the atomic spacing, and its predictions agree well with experimental measurements across a wide range of temperatures. Secret 66. Thermal expansion, the tendency of most materials to increase in volume as temperature rises, reverses in certain materials and temperature ranges, a phenomenon called negative thermal expansion. Water near its freezing point offers a partial illustration. Water reaches its maximum density at approximately 4 degrees Celsius and is slightly less dense both above and below that temperature, meaning it contracts when warmed from 0 to 4 degrees rather than expanding. This anomaly arises from the progressive collapse of an open, hydrogen-bonded structure that persists just above the melting point. In materials science, true negative thermal expansion over a wider range is observed in certain crystalline framework materials, such as zirconium tungstate, where geometric features of the crystal structure cause the lattice to contract uniformly as temperature rises, through a mechanism quite distinct from water's anomaly, but governed by the same underlying principle. that the relationship between temperature and volume is not always the one common experience would suggest. Secret 67. At temperatures near absolute zero, the electrical resistance of ordinary metals, not superconductors but conventional metallic conductors, decreases toward a residual value determined by the impurity concentration and lattice defects within the metal, rather than continuing to fall indefinitely. This residual value, called the residual resistance, reflects the scattering of conduction electrons by static defects in the crystal lattice that persist even when thermal vibrations are effectively frozen out. According to current theoretical models, a perfectly pure, defect-free crystal of an ordinary metal would approach zero resistance as temperature approached zero. Real metals always retain some residual resistance, reflecting the practical impossibility of perfect crystalline order. Secret 68. The magnetic behavior of matter at low temperatures encompasses various ordering phenomena in which the magnetic moments of individual atoms arising from electron spins align collectively throughout the bulk of the material. Ferromagnetism, anti-ferromagnetism, and ferrimagnetism are different patterns of this collective alignment, distinguished by whether neighboring moments align parallel or anti-parallel to one another, and by the geometry of the arrangement. These ordered magnetic states emerge below characteristic transition temperatures, the Curie temperature for ferromagnets, the Néel temperature for antiferromagnets, and their emergence is, according to current condensed matter physics, a phase transition governed by the same statistical mechanical framework that describes other phase transitions in matter. Secret 69. Quantum spin liquids, states of matter in which magnetic moments remain disordered and fluctuating even near absolute zero despite strong interactions between them, represent, according to current condensed matter research, a class of quantum phases with no classical analog. In an ordinary magnetic material, strong interactions between magnetic moments drive them into an ordered state at low temperatures. In a quantum spin liquid, the geometry of the interactions and the quantum character of the spins combine to prevent any ordered state from becoming stable. The system remains indefinitely in a fluctuating and tangled quantum state. These materials are the subject of ongoing scientific investigation, and available data does not yet give a complete picture of all their properties. Secret 70. The phenomenon of quantum coherence, the maintenance of a definite phase relationship between different quantum states of a system, is fragile at ordinary temperatures, where thermal fluctuations and interactions with the environment continuously disrupt those phase relationships. At lower temperatures, where thermal energy is reduced and the environment is quieter, coherence can be maintained for longer durations and across larger spatial scales. This extended coherence is what allows the collective quantum behaviors described in this section: superfluidity, superconductivity, Bose-Einstein condensation, to emerge and persist as macroscopic phenomena rather than remaining confined to the scale of individual particles. From Secret 44 through to Secret 70, we have moved through the quiet, solitary world of atoms. Quantum mechanics is no longer, at this point, a remote theory. It is the true face of matter, the one underlying reality. This section of the journey will bring together what we spoke about at the beginning, those distant stellar dusts and ice crystals, and draw them toward a single point of understanding. We return now to that still and quietly magnificent order, the place where matter simply continues as it is, where the laws of nature move forward in their own current without resistance. Toward the end of this journey, together. 30 secrets remain. We have moved through 70 together, side by side on this journey. I hope you've come to see the Sleepy Alchemy channel not as just another science sleep channel, but as something closer to a friend, a companion in whatever you might be carrying. Because alongside helping you drift toward sleep through science, I'm trying to draw you away from whatever difficulties your day or your life has brought, to be someone who sits with you in it, with the single hope of making you feel even slightly better, the way a close friend might. If even one person among you has found some distance from their troubles, some comfort, some steadiness of heart, that means more to me than anything else. If so, let's continue. Secret 71. Radiation pressure, the mechanical force that light exerts on matter, is, according to current electromagnetic theory, a direct consequence of the momentum carried by photons. Although photons have no rest mass, they carry momentum proportional to their energy divided by the speed of light. When a photon is absorbed by a material surface, that momentum is transferred entirely to the absorbing material. When a photon is reflected, the momentum transfer doubles. The photon reverses direction, and the material receives twice the push. This force is real, measurable under laboratory conditions, and consistent with Maxwell's electromagnetic theory, which predicted radiation pressure analytically before it was confirmed experimentally. Secret 72. The magnitude of radiation pressure under conditions near ordinary energy sources is vanishingly small by everyday standards, far below any threshold of ordinary mechanical perception. A surface completely absorbing sunlight at Earth's distance from the Sun experiences a radiation pressure of approximately 9 micronewtons per square meter, a force many orders of magnitude smaller than atmospheric pressure. Nevertheless, for objects with very low mass and large surface area, fine dust grains, thin films, individual atoms, this force is not negligible. According to current models of dust dynamics in the regions between planetary bodies, radiation pressure is one of the forces that shapes the spatial distribution of fine-grained material over long timescales. Secret 73. The interaction of light with individual atoms, the microscopic mechanics underlying radiation pressure at the atomic scale, involves discrete absorption and emission events governed by quantum mechanics. When an atom absorbs a photon, it transitions to a higher electron energy level and simultaneously receives the photon's momentum as a push in the direction of the photon's motion. When the atom subsequently emits a photon as it returns to a lower energy state, it receives a recoil impulse in the direction opposite the emission. Because emission occurs in a random direction each time, the recoil from emission averages towards zero across many cycles. But the absorbed momentum always points in the same direction, toward the source. The net effect, accumulated over many absorption-emission cycles, is a sustained force pushing the atom away from the light source. Solar sails, propulsion systems for spacecraft that use the momentum of sunlight rather than fuel, are, according to current aerospace engineering data, a practical engineering application of radiation pressure. The principle requires no fuel consumption. Sunlight continuously exerts a small but sustained force on a large, low-mass reflective surface, gradually accelerating the spacecraft. The acceleration is modest, but because it is uninterrupted and requires no propellant on board, it can, given sufficient time, produce velocities unachievable by chemical propulsion of equivalent mass. Several experimental solar sail missions have been carried out, confirming that radiation pressure is sufficient to produce measurable orbital changes in spacecraft designed for it. Secret 75. The Poynting-Robertson effect, a drag force experienced by small particles orbiting a star, arises from a subtle asymmetry in radiation pressure associated with the particle's orbital motion. A particle orbiting a star absorbs radiation arriving slightly ahead of its direction of travel due to the aberration of light, and emits radiation symmetrically in its own rest frame. The net result is a small but sustained force component opposing the orbital motion, causing the particle to lose angular momentum and slowly spiral inward. According to current orbital dynamics models, this effect is significant for particles in the size range of micrometers to millimeters across astronomical timescales, influencing the long-term distribution of fine material in planetary systems. Secret 76. Gravitational lensing, the deflection of light by massive objects, arises, according to current physical models, from the geometry of curved spacetime as described by general relativity. Light travels along geodesics, the shortest available paths through spacetime, and in the presence of a massive object, those geodesics are curved by the mass-energy distribution of the object. The result is that light passing near a large mass follows a curved path, arriving at a distant observer from a direction slightly different from what it would be without the intervening mass. The deflection angle is proportional to the mass of the deflecting object and inversely proportional to the closest distance of approach for light passing near a compact, massive body. Secret 77. The geodesic paths followed by photons near a very massive, compact object, according to the mathematical framework of general relativity, include, at a specific distance called the photon sphere, circular orbits in which photons travel in closed loops around the object. These orbits are unstable. A photon just inside the photon sphere will spiral inward. One just outside will spiral outward. The existence of the photon sphere is a purely geometric consequence of the mass distribution, a feature of the space-time geometry itself, not of any material force acting on the photon. Its predicted location depends only on the mass of the central object and the geometry of the surrounding space-time. Secret 78. The Schwarzschild radius, the radius at which the escape velocity from a spherical mass equals the speed of light, according to the solution of Einstein's field equations for a non-rotating mass, defines a boundary within which the classical notions of spatial distance and temporal duration are altered to an extreme degree. At this boundary, called the event horizon, the geometric distortion of spacetime is such that all geodesics, all possible paths through spacetime, point inward. The event horizon is not a physical surface. It has no material composition. It is a geometric boundary determined entirely by the mathematical structure of the field equations. Secret 79. The gravitational time dilation near a massive compact object, the slowing of clock rates in regions of strong gravitational fields relative to regions of weaker fields, is, according to general relativity, a geometric effect arising from the curvature of spacetime. A clock placed near a massive object runs slower by the measurement of a distant observer than one placed farther away. This effect has been confirmed experimentally using atomic clocks at different altitudes above Earth. Clocks at higher elevation, where the gravitational potential is slightly greater, run measurably faster than identical clocks at lower elevation. The difference is small under ordinary conditions, but consistent with the predictions of general relativity to high precision. Secret 80. The spectrum of light emitted near a region of strong space-time curvature and observed from a distant position is, according to current models of general relativity, shifted toward longer wavelengths, gravitational redshift. Photons lose energy as they climb out of a deep gravitational potential well, and the loss of energy corresponds to an increase in wavelength. This effect is independent of the nature of the light source and depends only on the depth of the gravitational potential well from which the photons originate. It has been observed in the spectra of compact stars and confirmed in precise laboratory measurements using gamma-ray sources at different heights, the Pound-Rebka experiment, which provided one of the earliest direct confirmations of this prediction. Secret 81. The frame dragging effect, a prediction of general relativity in which a rotating massive object pulls the surrounding space-time along with its rotation, produces small but measurable deviations in the orbits of nearby objects and in the paths of light. According to current models, Earth's rotation produces a frame dragging effect measured by the Gravity Probe B satellite mission, which detected the predicted precession of gyroscopes in polar orbit. The effect is extremely small near Earth, but becomes increasingly significant near more rapidly rotating and more massive compact objects. It is a purely geometric consequence of the off-diagonal terms in the space-time metric produced by rotation. Secret 82. Gravitational waves, propagating distortions of space-time geometry produced by accelerating masses according to general relativity, carry energy away from their sources at the speed of light. Their experimental detection in recent years through interferometric measurements sensitive to length changes far smaller than an atomic nucleus represents a direct measurement of space-time geometry changes produced by events involving very massive compact objects. The detection method relies on the same principles governing any interferometry experiment, comparing the travel time of light along two perpendicular paths, applied to length changes of extraordinary smallness. Secret 83. The cosmic microwave background, a thermal radiation bath filling the observable universe, according to current cosmological data, has a temperature of approximately 2.7 Kelvin and a spectrum that matches the black body radiation curve with extraordinary precision according to current measurements. This radiation interacts with matter primarily through Thomson scattering, the elastic scattering of photons by free electrons, and through the photoelectric and Compton effects at higher photon energies. According to current models, at the present density and temperature of the universe, this radiation passes through ordinary matter with very little interaction, rendering the universe largely transparent to it. Secret 84. Atomic clocks, the most precise timekeeping instruments currently available, according to current metrology data, operate by counting the frequency of electromagnetic radiation absorbed or emitted during transitions between specific energy levels of atoms. The cesium-133 atom, whose hyperfine ground state transition frequency defines the SI second, oscillates at approximately 9,192,631,777 cycles per second. This frequency is, according to current quantum mechanics, a stable property of the cesium atom determined by its nuclear and electron structure, the same everywhere and always to the limits of current measurement. Time within this framework is counted in the periodic structure of atomic physics. Secret 85. The fine structure constant, a dimensionless number approximately equal to 1 divided by 137, according to current physical measurements, governs the strength of the electromagnetic interaction between charged particles. It appears in the formulas describing the energy levels of atoms, the probability of photon emission and absorption, and the behavior of electrons in magnetic fields. Its precise value has been measured with extraordinary accuracy, and investigations into whether this constant varies across different regions of space or different epochs in the history of the universe have, according to available data, detected no statistically significant variation to date. The electromagnetic interaction appears, at current measurement precision, to be the same across the observable expanse of space and time. Secret 86. The molecular bond lengths of simple diatomic molecules, the equilibrium distances between bonded atoms, are determined at the molecular scale by the balance between electrostatic attraction and quantum mechanical repulsion. For the hydrogen molecule, this distance is approximately 74 picometers, 74 trillionths of a meter. This value has been measured spectroscopically with extreme precision and calculated theoretically to comparable precision using quantum chemistry methods. The agreement between measurement and calculation represents one of the detailed confirmations of the quantum mechanical description of chemical bonding. Secret 87. Isotopic substitution, the replacement of one isotope of an element in a molecule with another, changes the molecular mass without altering the electronic structure, since isotopes differ only in the number of neutrons in the nucleus and have identical electron configurations. Because the vibrational frequencies of molecules depend on the masses of the atoms involved, heavier atoms vibrate more slowly. Isotopic substitution shifts the vibrational spectrum of a molecule to lower frequencies in a predicted, calculable way. This predictability is used in the spectroscopic identification of molecules containing specific isotopes and in the investigation of reaction mechanisms, where isotopically labeled molecules can be tracked through a series of chemical transformations. Secret 88. The van der Waals radius of an atom, the effective size of the atom when not chemically bonded, defined by the closest approach distance to a non-bonded neighbor, reflects the spatial extent of the outer electron cloud and the balance between attractive and repulsive intermolecular forces. These radii are not sharp boundaries. They represent the distance at which the repulsive component of the interaction between two non-bonded atoms becomes dominant. The concept is practically useful for understanding molecular packing in crystals, the accessibility of reactive sites in large molecules, and the physical properties of liquids and gases in terms of the effective molecular volumes occupied by their constituent particles. We continue quietly. You are welcome to listen to what follows in whatever way feels natural. As we have said from the beginning, nothing is being asked of you. Simply resting is more than enough. If your body has been at ease this far, I hope it remains so, peaceful, unhurried, gently held. We have now reached 88 of the 100 secrets, a considerable distance traveled together. I hope the journey has been something you've found worth taking. The final 12 secrets will be offered the same way, slowly, quietly, with nothing required of you in return. The video has not yet ended, but we are drawing close to its close. One of the things I have wanted to carry to you throughout this journey is this: you are not alone. However strongly you may feel that way at times, I never want that thought to settle in and stay. It is, in truth, a common feeling, something that moves through all of us at one point or another. But I believe, genuinely, that there is always someone willing to listen. And at the very least, know this: we are here. The Sleepy Alchemy family is here. Whenever you need it, this channel and these videos are something you can come back to. This channel will do whatever it can to leave you feeling a little better, because you are valued and you are loved. I hope I've managed to share that with you in a way that landed. If so, let's continue. Secret 89. The bond dissociation energy of a molecule, the energy required to break a specific chemical bond and separate the molecule into fragments, is a precisely measurable quantity that reflects the depth of the potential energy well in which the bonded atoms sit. Stronger bonds have deeper wells and higher dissociation energies. The carbon-carbon triple bond in acetylene, for instance, has a dissociation energy of approximately 835 kilojoules per mole, considerably higher than the carbon-carbon double bond, which is in turn higher than the single bond. These differences in bond energy translate directly into differences in chemical reactivity. Molecules with stronger bonds require greater energy input to initiate reactions and persist longer in environments where that energy is not available. Secret 90. The persistence of certain molecules across geological timescales, the survival of organic compounds within ancient mineral matrices, the stability of certain crystal structures over millions of years does not reflect any exceptional character of those particular molecules. It reflects the ordinary operation of thermodynamic stability under specific conditions of preservation. A molecule survives not because something is protecting it, but because the reactions that would convert it into something else require either an energy input or a reactive partner that the environment does not supply. Stability in chemistry is always conditional on environment. The molecule continues because the conditions for its change are not met. That is the complete explanation. Secret 91. The half-life of a radioactive isotope, the time required for half of a given quantity of that isotope to undergo radioactive decay, is, according to current nuclear physics, a stable property of the nucleus, determined by the balance of forces within it. It does not depend on the atom's chemical environment, its temperature, its pressure, or the history of the sample. A nucleus either has sufficient internal energy to decay within a given time window, or it does not. This independence from external conditions makes radioactive decay one of the most reliable clocks available for measuring elapsed time in geological and astrophysical contexts, not because the physics is exotic, but because it is exceptionally consistent. Secret 92. The stability of atomic nuclei, the property that determines whether a given combination of protons and neutrons produces a long-lived nucleus or one that rapidly disintegrates, is governed by the balance between the strong nuclear force, which holds nucleons together at very short range, and the electromagnetic repulsion between protons. Nuclei with too many protons relative to neutrons experience a net repulsion that exceeds the binding capacity of the strong force and are unstable. Nuclei with an imbalance of neutrons relative to protons find pathways toward greater stability through decay processes that adjust the ratio. Stable nuclei, those that have persisted since their formation, occupy a narrow band in the space of possible proton-neutron combinations known as the Valley of Stability. Secret 93. Gold occupies a position within the Valley of Stability, and its most abundant isotope, gold-197, with 79 protons and 118 neutrons, is, according to current nuclear data, stable against all known decay pathways. It does not spontaneously convert into another element. It does not emit radiation under ordinary conditions. The nucleus is bound with sufficient energy that no internal rearrangement exists that would lower the system's overall energy. Gold-197 continues as gold-197 indefinitely to the limits of current physics, not because it is exceptional among elements, but because that particular proton-neutron combination happens to sit in a region of the stability landscape where no decay pathway is energetically favorable. Secret 94. Gold's electron configuration, specifically its filled d-orbital subshell and single outer s electron, produces, through the relativistic contraction described earlier in this exploration, an unusually high ionization energy for that outer electron relative to silver and copper, which occupy the same group in the periodic table. This elevated ionization energy means that gold's outer electron is less available for bonding than those of its periodic neighbors. The chemical consequence is reduced reactivity. The aesthetic consequence, observed and made use of throughout recorded human history, is a surface that preserves its optical properties indefinitely under ordinary conditions, neither oxidizing nor tarnishing. According to current quantum chemistry, gold's color is itself a relativistic effect. Without orbital contraction, gold would be predicted to appear silvery white, like most metals. The yellow color arises because the relativistic contraction of the s orbital shifts the energies of certain electronic transitions into the visible range, causing gold to absorb blue light and reflect the remaining wavelengths. Secret 95. The reflectance spectrum of a material, the precise wavelength by wavelength distribution of how much of the incident light it reflects, is a direct consequence of the electron structure of its constituent atoms and the crystal structure of the solid they form. Two materials with identical chemical composition but different crystal structures, diamond and graphite, both pure carbon, have entirely different optical properties because their different bonding geometries produce different electronic band structures and therefore different interactions with visible light. Diamond is transparent at visible wavelengths. Graphite is opaque and metallic in appearance. The atoms are identical, the structure differs. The optical behavior is transformed entirely. Secret 96. Surface chemistry, the chemical behavior of the outermost atomic layers of a material, which differs from bulk chemistry because surface atoms have fewer neighbors and therefore unsatisfied bonding capacity, determines how materials interact with their environments at interfaces. Gold's corrosion resistance is, in part, a surface chemistry phenomenon. According to current surface science data, the energy barrier to forming gold-oxygen bonds at the surface is high enough that ambient oxygen does not react with gold surfaces at ordinary temperatures. Other metals, iron, copper, aluminum, have surface chemistries that permit and even facilitate oxidation under the same conditions, leading to the formation of oxide layers that progressively alter the surface properties of the material. Secret 97. The preservation of materials in environments of low chemical activity, low humidity, low temperature, absence of reactive gases, reflects the straightforward operation of chemical kinetics. As temperature decreases and the concentrations of reactants diminish, reaction rates slow. Materials stored in such environments degrade more slowly, not because the preservation chemistry is exotic, but simply because the conditions for degradation chemistry are not met. The material persists in a state of kinetic stability, perhaps not at thermodynamic equilibrium, but in conditions where the path to equilibrium is so slow that, across any practical timescale, persistence and stability are indistinguishable. Secret 98. The infrared emission of all objects above absolute zero, thermal radiation described by Planck's law, means that every material surface continuously emits electromagnetic radiation at wavelengths determined by its temperature. At room temperature, this emission falls primarily in the mid-infrared range, invisible to the human eye, but detectable by appropriate instruments. The total power emitted per unit area scales with the fourth power of absolute temperature, a relationship known as the Stefan-Boltzmann law. This continuous emission represents a flow of energy from every object into its surroundings, a slow, sustained, and entirely passive exchange in which every object participates simply by virtue of having a temperature above absolute zero. Secret 99. Carbon chemistry. The element whose bonding flexibility underlies the structural complexity of organic molecules arises from a combination of properties that are not individually unique to carbon, but together produce an element capable of forming an unusually wide range of stable structures. Carbon forms 4 covalent bonds. Those bonds can be single, double, or triple. Carbon atoms bond readily to one another, forming chains and rings of arbitrary length and complexity. The bond energies involved are high enough for carbon skeletons to remain stable across a wide range of conditions. And the small size of the carbon atom allows close approach between bonded atoms, producing precise geometries that give organic molecules their characteristic three-dimensional structures, and with them, their characteristic chemical and physical properties. And the 100th and final secret: the persistence of matter, the property that has appeared in various forms throughout this exploration, from the molecular patience of chemistry suspended in cold interstellar dust to the nuclear stability of gold's nucleus, from the quantum coherence of superfluid helium to the crystalline endurance of molecular ices, is not a property that matter possesses through intent or design. It is matter's natural condition when there is insufficient energy to change it. Every stable structure, every unreacted molecule, every intact crystal lattice represents a system in which the available energy is insufficient to overcome the barrier to change. Stability is not active, it is the default state when conditions permit. And conditions across wide regions of the observable universe and across timescales far exceeding any human frame of reference very often do. Matter continues because physics does not require it to do otherwise. That, according to current scientific understanding, is the complete and sufficient explanation. 100 molecular details have passed through this space, descending from the organic chemistry of cold interstellar dust clouds, through the fluid dynamics of plasma and gas, through the geometry of crystalline ices, through the quantum inertness of noble atoms, down into the physics of matter approaching absolute zero, and back out through the mechanics of light and the geometry of space-time, arriving finally at the continuing chemical logic of stable matter. None of it hurried. The details ask nothing of you. They want nothing. The primary purpose of this video was always for you to rest and to drift gently toward sleep. Sharing knowledge was the secondary aim, to help you toward sleep by way of it. But what matters most to sleepy alchemy is your comfort and your well-being. Your room is quiet now, in all likelihood. And isn't that the finest thing? To fall into peaceful sleep in a quiet, darkened room. The molecular architecture of everything in that room, the materials of the walls, the surface of every object, the air itself, continues its patient, low-energy chemistry, exchanging heat with its surroundings at the rate the temperature difference permits, maintaining its structural integrity because the conditions for change are not present, persisting in exactly the configuration that physics allows. That persistence asks nothing of the body resting here in peace. Rest, according to current scientific understanding, is not the absence of chemistry. It is a different chemistry, lower in energy expenditure, slower in its cycles, but orderly and uninterrupted and sufficient. The molecular processes moving quietly through a resting body do what they have always done, without instruction, following the same physical logic that governs matter everywhere it has been explored. Nothing needs to be done with that information. Nothing needs to be done at all. If at some point during this exploration one particular detail held your attention a little longer than the others, the molecular patience of chemistry suspended in cold dust, the frictionless flow of superfluid helium, the geometric completeness of the noble gas electron shell, the unchanging color of gold's relativistic electrons, that detail is welcome to stay wherever it has settled. It belongs to no test. It leads nowhere in particular. It is simply a small, precise piece of the physical world, sitting in its place within the structure of what is currently understood about matter. If something caught your interest, raised a question, or gave you a thought you'd like to share, I would be genuinely glad to see it in the comments. And if you'd like to help Sleepy Alchemy reach more people, a like and a subscription go a long way toward growing this community. We have reached the end of the video. I hope that by now you are already resting peacefully. May this sleep clear away the stress and concerns of the day and leave you ready to meet tomorrow with a little more energy, a little more lightness. Thank you for being here with us through all of this. As I always say, you are valuable and you matter. Never forget that. Whenever you want to rest again, to find that quiet and drift gently toward sleep, Sleepy Alchemy will be here. Good night. Take care of yourself. Until next time.